Today's webinar is brought to you by Transcat and Megger. Welcome to Fundamentals of Insulation Resistance Testing. I am your moderator, Meredith Kenton, the Digital Marketing Specialist here at Megger. If you have any questions about webinars in general, please feel free to reach out to me via email or phone. And if you have questions regarding the information presented in today's webinar, please call the Megger Transcat hotline at 1-800-233-6540. Again, if you have application questions about today's webinar, please reach out to the Megger Transcat hotline directly. And on that note, I would like to introduce Jeff Jowett, today's presenter. He is our Senior Applications Engineer here at Megger. If you have questions specific to the material covered in this presentation and you thought of it after you didn't get a chance to ask, I encourage you to reach out to Jeff directly. And on that note, Jeff, it's yours.
Good morning, everyone. Welcome to our webinar on fundamentals of insulation resistance testing. This is a rather large subject. We won't go into techniques today. That will be next week. And so we do encourage you to sign up for that one as well. Today's just fundamentals primarily because insulation properties and the testing of it are considerably different than a large bulk of electrical testing that many of you may have been doing for years, working with equipment like DMMs, for instance. And it's very important to understand these differences and know basically how the effects they have on your test results and how to deal with them and so forth, because otherwise insulation testing can be really confusing and counterproductive. And always keep in mind, not just during the next hour, but when you're out on the job, relate things back to Ohm's law. The testing is fundamentally, the basis of it is quite simple. Once you get into the various techniques and so forth, it then becomes somewhat complex, but that's all got an underlying basis in Ohm's law, and so it helps when you're on a job and you're up against a question of some sort. It always helps to just think about, well, how does Ohm's law apply to this situation, or how does it apply to the answer I'm looking for? And that can very often help you work your way mentally through an issue. No insulation is perfect. This is important to realize just from the very start. The old insulation testers from years ago, which many of you, I'm sure, have used and are familiar with, the old analog units, they had an infinity symbol up on the high end of the scale. That's not a measurement. That just meant that the resistance that you're trying to measure is greater than the capabilities of the tester. Those old testers, and a lot of them still on the market, common ones, go to about 1 or 2 gigohms, which is 1,000 megs. So typically you'll get 1 or 2,000 megs maybe out of a fairly off-the-rack insulation tester. And at that rate, the common lexicon that got into our market was thinking in terms of infinity, as if that represented some sort of perfect insulation, but actually doesn't. It's just an overrange symbol. So keep in mind, a good illustration will be a lightning strike. Air is a good insulator, but you put enough voltage between the cloud and the ground and you get current flow. And so the same thing applies to any other material. You put enough voltage on it, you can get current flow. And that's the basis of how an insulation test is performed and what we'll be seeing as a test result. So then a seemingly simple question, but it actually is, as we'll see as we'll go along, is really rather complex, is what actually is good insulation? And the answer to that is not at all straightforward. It's pretty varied, and we'll pretty much cover it this morning. But fundamentally, good insulation is the value that you need for your equipment to be safe and operate properly. And also, you want to be able to keep a good reading. because insulation will deteriorate over time. And that's part of the reason that you test it, and we'll come back to that again and again. These are the common factors that you deal with in the workplace that deteriorate insulation and make it break down and make equipment fail. Mechanical damage, things like the stretching of cables by robots and so forth, or dragging cables across a floor. Mechanical vibration has an enormous effect on the insulation of the equipment that is surrounded by some piece of equipment that's vibrating in its normal operation. Heat and cold, we'll come back to them. The factor of temperature, we'll come back to it again and again. It's huge. And then, of course, in industrial and other work environments, you get a lot of dirt, oil, corrosive vapors, things like that are common in a lot of environments and will penetrate the insulation. Moisture is huge. You can get that in, of course, in a flood, but that's an extreme example. But in just normal operating procedures, very often in factories or other types of environments, there's some process maybe running nearby that is putting excess moisture into the environment, and your insulation will gradually over time absorb that. Very often a workable solution to a problem is just to put up some kind of a moisture shield around a motor or around some other piece of electrical circuitry. And then finally, humidity has a profound effect. We'll talk about that as well. Given long enough and enough operation, and insulation will eventually fail. You'll see we'll keep coming back to these three major categories of problems: mechanical stresses from operation, physical operation, electrical stresses from primarily things like startups, surges, and voltage spikes that occur from disturbances on the line and so forth, present electrical stresses, and then the environmental stresses from corrosion and moisture and things like that. And what are you trying to avoid then with insulation deterioration? Well, the first thing that is, of course, human safety. If insulation breaks down and shorts out, the human can become the path to ground and be injured or electrocuted. So we want to eliminate that possibility from your living or working environments. There is also electrical fires. Now, a lot of people may think, well, what about the breakers tripping and so forth? Isn't that going to protect me? Well, fundamentally, of course, it does. But there are additional hazards. And one example can be in a piece of equipment where you have electrical circuitry and a motor or whatever is operating, and it's got casework around it. And there's very narrow tolerances in many cases between the circuitry and the surrounding casework. And in the environment in which it's operating, dirt and corrosives and oil and things like that may build up, and you get that promotes the flow of leakage current, and it's trapped in a relatively narrow space. It's not enough to trip your breakers, but heat is gradually accumulating, and you can get spontaneous combustion of things like oil and dirt, and that's where a lot of your industrial fires begin. And then the final point there is unscheduled downtime. You just don't want to have breakdowns in operation, which can be very costly. And instead, by an insulation testing maintenance program, you can kind of get an idea, predict when that scheduled that downtime may be starting to get near, and so you can have scheduled downtime to do preventive maintenance. So we'll come back again and again to good and bad. We'll refer back to these parameters and how you determine them and how you evaluate them, and we'll make constant references back to the effects of temperature and the effects of moisture. Now, when a piece of equipment is made, these are the variables that occur during its construction. And so this is what you get when you buy something. And so that's your starting point. And very often you can see specifications on a piece of equipment that you bought. and that put and installed, and that those specs may be very important to its future operation, so kind of keep them handy. And then once you're in service, then these variables day to day start to come into effect. And so cleanliness, moisture and temperature, and mechanical damage are all parameters that are going to, they're kind of ongoing effects on your equipment and can be reflected in your insulation resistance readings and give you an evaluation of the condition of the equipment. Okay, temperature. A marked effect on insulating values. A reason for this is because as temperature goes up, of course, the agitation of molecules increases, and that helps to promote current flow. And so insulating materials are principally made up of very large, very complex and polar type of organic molecules. And as they become agitated with temperature, then the leakage current through the insulation increases. As a general rule, we'll come back to this again several times, but this is just to give you a general idea. 10 degrees centigrade increase in temperature typically cuts insulation values about in half. So you can see it's quite pronounced. And there's just some other points about, again, very important, and we'll touch on it again and again, correcting to common temperature bases. The main thing you take away from this particular slide is that you can find in the specifications of equipment, you can find a temperature correction factor. And that's just a number that relates to the specific type of insulation that your motor or whatever it is has around it. And you use that temperature correction factor to establish a common base so that you can compare your readings one to another over weeks, months, years, whatever. And the readings are comparable and easy to interpret if they're corrected to a common base. Okay, types of tests. Before we go into the instrumentation and the testing, it's always important at the beginning of a job to just take a couple of moments to think about the goals of your testing and to plan a little bit. And there are two major testing goals where insulation testing is concerned: the go, no go, or pass fail type of test, and the diagnostic type of test. So it's helpful to just think, which are you going to do? Go, no go, that very often will be your breakdown testing. Something has failed. A motor, for instance, has tripped out the breakers. You're trying to determine where the problem is. You're trying to isolate a weak point somewhere in your circuitry, and that's a go, no go type test. So for that, you can generally just use a basic insulation tester. You don't need a whole lot of range. One of the major determinants in an insulation tester is how high it will measure. And so in this century, the values have gone all the way up into the teraohm measurement range, and you can very easily buy an insulation tester that will measure up into teraohms. The common unit of measurement, of course, is the megohm, 1,000,000 ohms, and that's what is most commonly used in insulation, megohm readings. But 1,000 megohms goes into the gigohm range, and then 1,000 gigs is up into the teraohm range. So you can see that's absolutely enormous, far beyond the measurement ranges of most types of electrical testers. And so for a go, no go test, a common, relatively inexpensive tester will generally run up to a gigohm or two. And as far as I know, I can't think of anything that's bad at a couple of gigohms. So that's all you really need, and you don't necessarily need an expensive or highly developed tester to do go, no go testing, where you're just trying to find out, is something bad or not, or what is bad or not. But diagnostic testing, on the other hand, that's where you really want to have a full-featured unit. You want to be able to measure insulation when it's still very early in its life cycle, the equipment that is, and you want to be able to get an idea where a piece of equipment is along its life cycle, and we'll come back to that. And for that type of testing, you do want to have a full-featured unit. Okay, so what about diagnostic testing then? Why do we do this? Well, we have the concept of predictive maintenance. In other words, you can trend your test results over time, and you can see is something dropping rather precipitately in its readings. In which case, you may be able to install some protective device like a moisture shield around a piece of equipment, and may alter that drastically. You can adjust maintenance activities. So in other words, rather than during a shutdown, just having to test everything, you can get an idea of the equipment that's very early in its predictive life cycle, and you don't need to bother to test it right now. Look at the stuff that's well along in its life cycle and test that. So you can adjust your maintenance activity and make it more practical. And you don't necessarily have to rely on fixed maintenance and we're going to test this every 6 months. We're going to test it every year. You don't necessarily have to do that. If you're up in the teraohm range, you really don't have to worry about that for a while. But the equipment that's down, approaching 100 megohms or whatever, that's what you want to look at. So that's adjusting your maintenance schedule, and you can make much more practical use of your time, let's say. So 2 key rules: test periodically, adjust your conditions. We'll come back to this again and again. Your test conditions have an enormous impact, so you don't want to let the conditions rule your results. You want to correct for them, and then you want to keep records. In the old days, they used to have what was called a test record card that would hang on in a protective plastic jacket on a piece of equipment, and you would hand write the results in. Now you don't have to do that anymore. Now you press a button on the tester and it stores your results, and it goes into a program that you can download to your computer, and you can make it complicated, you can make it simple, whatever you prefer. You have a lot of very effective data manipulation that's available at your fingertips. Okay, so now we're going to take a look at the particular piece of equipment, the fundamental design of an insulation tester and how it operates. That last bullet there about independent of actual test voltage, that's somewhat archaic, but those of you who've been in this industry for a while will probably remember that, and there are still some of them out there. The older testers, you used to have one fundamental direct measurement at a specific voltage, usually 500 volts, and then any other voltage, you would have to apply a multiplier or a divider to adjust your reading. Well, you don't have to do that anymore. All the new testers are direct reading. What you see is what you get. Okay, so now what we're going to look at here is that the fundamental operation of the insulation tester. It applies a test voltage across your test item. The voltage pulls a certain amount of current through your test item, and then those 2 parameters in Ohm's law, like we said at the beginning, calculates out the resistance, and that's what you see now on your display. It's a fundamental schematic of how an insulation tester operates. The G in the middle, that's a guard circuit, a guard terminal. You don't ever have to use it. You can if you wish, and we'll talk about that at the end of the presentation, but you don't have to use it. It's a shunt circuit. Sometimes people confuse that. They think it's a ground and you're putting a safety ground. If you do that accidentally, it won't do any harm, but it'll just get in the way of your test measurements. That's all. So don't use it as a ground. We'll talk about how you use it as a guard. But fundamentally, you've got a plus and a minus terminal. All insulation testers are DC units. AC units are typically high pots. They're typically used to actually break down the test item so that it won't go into service and let you down. Totally different type of measurement. Insulation test is a DC tester. And what we show here is your negative terminal is connected by an alligator clip to your circuitry, and your positive terminal is connected to a return. Now, that is not the insulation. You never clip your alligator clip onto the insulation itself. That really won't do any good. But what you're looking for is some sort of metal conductor. So that could be a sheath or a shield or another conductor or whatever. And so now your insulation is between those two poles. And when you apply your voltage, a certain amount of current is going to pass through the insulation and complete the circuit. And that's what you're going to see up on your display. And just as a quick note, industry standard is to do negative to circuitry, positive to return. No longer, years ago, it mattered more. Modern insulating materials, not so much anymore. You don't get a polarity effect. And so if you accidentally hook it the other way around, you don't have to throw out your test results. So it's okay. But mainly you want to follow industry standard for the benefit of third-party involvement. So industry standard is negative to circuitry, positive to return. And applied test voltages. Well, there are different recommendations that you will see in different standards and in SOPs and so forth. So you may need to follow an SOP, but in general, your equipment like telecom, datacom tests at lower voltages, 50 and 100 volts. For building wiring, 250, 120, 250, 480, 600 volts. All of that type of circuitry typically is tested at 500 volts. That's kind of industry standard for maintenance tests, and for troubleshooting where you're looking for a problem, then you typically run it at 1,000 volts or twice the normal maintenance test. And then for what is called medium voltage equipment, when you get up over 1 kV rated, then you test at typically 5 kV or some higher voltage in that range. But note that the standards agencies have noted that for equipment that's running well up into medium voltage, you can't be expected to have an expensive, heavy insulation tester that puts out 50 kV or something like that. So typically, if you get up around 15 kV, you're good to go on just about any type of equipment to test the insulation values. Okay, we're going to talk about the readings now and how to interpret them. And interpretation of readings is not easy. It's not like using a DMM. It's not, it's not like measuring voltage on a circuit or something like that. There's a lot more to it. And so a good bit of this presentation is going to cover that. Now we're going to look at the currents. When you apply your insulation tester, you're going to get 3 currents are going to flow: capacitance, absorption, and conduction or leakage. And the tester is going to see them all, and it's going to base your measurement on all 3 currents. Just keep in mind, on insulating material, it tends to be polar. If you apply a DC gradient across the insulation, then the polar molecules are going to align themselves against the field. And this is a movement of charge, and hence it is a current. And it is critical in applying your test and interpreting your readings. And this is a graphic then of how your various currents behave during the course of an insulation test. So capacitance is real quick because that's in the metal. A big motor winding has a lot of capacitance, but because it's in the metal, it charges up very quickly and goes away. Absorption is the same phenomenon, but it happens in the insulating material. And since that is not a conductor, and so it tends to take a lot longer. With very large equipment, that can take a prodigiously long time, actually. And so there are ways of dealing with this. Leakage current, on the other hand, that's what you're interested in. That's what's getting through your insulation. And that behaves differently. And so it charges up relatively quickly and then maintains constant at the same voltage. And what your tester is measuring is total current. And at some point over to the right, the two charging currents have dropped out. And the total current is all you're seeing. But that, on big equipment, that can take a rather long time, and you may not want to have to test for that long. And when we get to next week, when we go to procedures, we'll show you how to deal with that. Okay, so that's a quick summary then of what the currents are doing against time. And so note that the time of the test is critical, and also keep in mind that the temperature is also highly critical to the reading that you're going to see on your display. And we can go through these relatively quickly. This is just to give you, kind of put you on home base here with a look at some of the types of equipment that you'll be testing. Any type of electrical equipment, of course, is subject to an insulation test. These are some typical examples of low capacitance devices. These are going to charge up relatively quickly, and your readings are going to stabilize more quickly. And these are some high capacitance items, which can take a very long time to go to full charge. And really, the principal difference you see between them is size, the amount of insulating material that's involved. And the construction is also important to a considerable degree as well. But the main factor is just the size and how much insulating material is involved. Okay, test procedures. One thing you don't want to do, and this is a common call that comes into the factory, is just fly blind and hook up a couple of leads and press a test button and get a reading. That is not going to tell you a whole lot, and in fact, it could even mislead you. So that's why it's a good idea to attend webinars like this one and the one we'll give next week on techniques. And then that'll put you on home base on how to interpret what you're seeing, because insulation testers are radically different than DMMs, where generally, you see you got 122 volts or you got 1.5 amp of current flowing. There's not a whole lot of interpretation that needs to be done there, but with an insulation test, there's a lot of interpretation. Now, the various procedures, like I said, we're going to cover them next week. We're only going to touch on them this week. This is a fundamental representation of what is called a spot reading test, which is basically just the simplest one. It's hooking up your alligator clips, pressing your test button, and getting a reading. So note that the reading is going to change over time, and it's going to go higher. And the reason it's going higher is because your charging currents are dropping out, and you're going to eventually all leakage. And so this is why the time of the test is critical. So note that at 60 seconds, you would get one reading. If you were down at 30 seconds and you were in a hurry and you got a reading at 30 seconds, you'd have a lower reading. So if you don't take that into account, then let's say someone else comes along later on and tries to repeat the test, but they only do it at 30 seconds, and they're going to get a much lower reading, and they're going to think that something drastically went wrong here, when in fact, no such thing occurred. So when you're recording results and when you're reporting the results of a test, put your time of the test as part of your result, so that anyone following behind you can properly interpret how you reached that result, that you got 50 megohms at 60 seconds, or you got 100 megohms at 30 seconds or whatever. So time is very critical in test reporting and in keeping records. The spot reading test is a good test for small equipment because you're going to come to full charge relatively quickly and have your final reading. But other test methods that go into more depth give you more information than you would just get out of a short time or spot reading test. But if you remember, we mentioned at or early in the webinar, we mentioned go no go type testing, and generally a spot reading test is probably all you need for go no go. If you're trying to meet a standard, let's say telecom, for instance, they install a circuit, they want to see 100. Typically, I think it's industry standard. They want to see 100 megohms or more. If they don't get that out of a newly installed circuit, they're not happy. So, okay, you do the test and you pass 100 megohms, you're done. You can move on. Or similarly, looking for a problem. You spot where the problem is, or you see that a piece of equipment is not the problem because it's well up in the megohm range, and you stop and you can move on. But for more analytical type of procedures, then typically you do want to use a more in-depth method, which will be discussed next week. So time resistance measurements, they compare two or more readings over time. And so that gives you more information, gives you more depth in the interpretation of your reading. So this is just a quick representation to show you. Good equipment typically is looking at mostly charging current, and so the readings keep going up. Equipment where there's a lot of leakage current, what you don't want, that holds down your reading. It keeps it relatively flat. So the lower reading here would be representative of equipment that has a problem, and maybe you want to get the moisture or the dirt out of it. And this is just to show you that if you took more than one reading and compared them, you could spot the difference between equipment that keeps rising with capacitance and absorption, whereas equipment that flattens out because of leakage. Okay, that's a quick look at test procedures and interpreting them, and mainly it's to just show you that simply hooking up and taking a reading is really not what you want to do, other than possibly in a go no go type test or meeting a particular standard. Now we'll look at the guard terminal, and we mentioned that early in the presentation, and we'll take a look at what you can do with that, which is an enhancement of your test results. Okay, so this shows a kind of a simplified circuitry here of a cable termination, and you've actually got two leakage paths here. You've got current that flows through the insulation, goes to ground, let's say, or current that can travel across the surface of the insulation. And the more moisture and the more contamination that there is, the more current will travel across the surface. And so you may want to have that in your reading, and you may want to take it out. So the guard terminal gives you the opportunity. You don't have to do it, but it does give you the opportunity to deal with this. So here would be an example of a fundamental application of a guard terminal. Now, here you're at a cable termination. Your two alligator clips, plus and minus, are pulling current through the insulation, and they're also pulling current across the surface of the insulation. You take a bare copper conductor, wrap it around, and run that back to the guard terminal. And now what's going to happen then is that will collect all the current that's traveling across the surface, and will shunt that back to your measurement module and take it, and it then removes it, the measurement module removes it from the reading and only looks at how much current is going through the insulation. And so you hook up your guard terminal and you see that your resistance reading goes up considerably that's telling you that there was a lot of surface leakage involved. This is looking at the same thing now through the instrument's viewpoint. Note that we have two parallel circuits here. We got the resistance that's going through the body and the insulation, and in parallel with that, we've got the surface leakage. And so if you didn't have the guard terminal hooked up and you just ran with your plus and minus terminals, then both of these paths are going to pass current, and the tester is going to see the totality of that current, and that's going to be the measurement that you're going to see. Now, if you hooked up the guard terminal, now that leakage path to the left is going to be removed from the measurement. And now the only thing that your display is going to be showing you is the leakage path to the right. Here's a good example of a very practical use of a guard terminal. This would be on transformer bushings. And what they found was that a lot of times these of course, are typically outdoors, and there's moisture and dirt traveling over the surface of the bushing from the minus to the positive terminal. And tests would be performed, let's say, in the morning when there was morning dew on the bushing, and the readings would be comparatively low. And so that would mislead the operator to think possibly the bushing is bad. It may have been hit by lightning. There could be a crack in there. And the crack doesn't have to be visible to the naked eye. Minuscule amounts of distance provide a path for current to flow. And so it doesn't have to be visible, and yet it can defeat the purpose of that bushing. So the utilities found, I guess years ago, that these bushings would be removed and they'd be taken back into the shop, and then they'd be retested in a warm, dry environment in the afternoon, and they'd be fine. And so they kind of wasted their time. And so you can actually buy on the market what is called a bushing guard spring, and you wrap that around or slip that down over the bushing and connect it back to the guard, and all of that surface leakage is now shunted out. And the only thing that the operator is going to see is how much current is getting through the body of the ceramic. And so now you get a good high reading. You tell the bushing is fine, leave it alone, and go on to the next job. So these are a couple quick steps then for preparing to run your test. Note up top, take out of service. Insulation tests are always performed offline. You do not run an insulation test online. So take the equipment out of service. You can get interference from surrounding equipment, especially if you're in a high noise environment like something like a switchyard, for instance. And so you do want to watch out for that. You do want to familiarize yourself with that possibility. Determine what's to be included in the test. Just hooking up randomly can give you readings that lead to misinterpretation. So plan ahead and think about what is the actual circuitry that you're measuring. What are you hooking across, and what is the tester actually going to see with those, between those two alligator clips, or between the alligator clips and the guard circuit. Discharge of capacitance. This is very important at the end of the test. This is your primary safety feature with doing an insulation test. What goes up must come down. So since this is a DC test, and we've already mentioned charging up the test item, charging the capacitance and charging the absorption current in the insulating material itself, that can be dangerous. However, now in the old days, the old testers, they used to have very often a discharge switch on them. And what happens if the operator is in a hurry and he forgets to punch the discharge switch? Then he could be in trouble because the operator doesn't want to be part of the discharge. So all the modern testers now have an automatic discharge feature built into them. As soon as you disengage the test voltage, now you've got voltage on the test item. The tester sees that and it tells the operator and it discharges it. So make sure that anyone doing an insulation test is made familiar with this and made aware to just watch the display and be careful of the discharge. Okay. And then, of course, we do mention that you could have noise from surrounding circuitry. And again, your modern testers will tell you in the old days it was pointer swing, and the pointer would be pointing back and forth, and that would kind of tell the operator, uh-oh, I'm picking up noise from someplace. Now the tester actually evaluates it and tells you. So the operator has a lot of these additional safeguards in new equipment. And finally, our last minute or two before we go to questions, interpreting values. This is tough because the values, like I said, they can run all the way to the terohms. But the basic old 1 megohm rule that you still see mentioned in the literature for equipment running off of building wiring voltages, you do not want to see less than a megohm. If you're down, most testers will have a kiloohm range on the bottom, and that's for helping you recondition equipment and things like that, where you measure down in the thousands of ohms. But if you're below a megohm, that shouldn't be in service. And then for equipment that is up at higher operating voltages, it's 1 megohm per 1,000 volts. So something that's operating on 1480 or something like that, you'd want to see 2 megohms and so forth. So you base your megohm interpretation on the operating voltage of the equipment that you're testing. And that keep in mind, however, that that's a drop dead value. That's just telling you this is worst case. This, you don't even want to put it in service. It could be a hazard of some sort or other. But for better interpretation of what you're actually seeing, of course, you do want to be able to interpret, well, what's 100 megohms, what's 1,000 megohms, and this information is all available in the literature to go into greater in-depth interpretation. But the best possible interpretation of a test result is if you have a record of a previous test. If it was good the last time you tested it, you didn't take it out of service, and you're holding that value, you don't have too much to worry about, even though it may not be terribly high, because you could have distributed leakage, which is where the insulation is just passing a relatively constant amount of leakage throughout the body of the insulating material. And that's not all that bad. It's where you have concentrated leakage, where there's a bad spot somewhere, that's going to break through the ground and eventually. So that's what you have to worry about more so. And so if you're holding your insulation resistance value, even though it's not terribly high, maybe it's 100 megohms or something like that, but you're holding it, don't worry too much. But if it's dropping relatively precipitately, that's where it's going to break down and it's going to short out the ground. And so that's a bigger concern. Okay, and with that, I think we've come to the end of the verbal presentation. And now we're going to go to questions. And thank you very much for your attendance.